quickly from Friday or Saturday. If you did not watch the video from Saturday, you need to because it has all the bond angles on it. If you're here Saturday, you're in luck. You know it all. Okay, so we're probably going to not get to the nuclear quiz at the end of class, so I'll open it tomorrow and have you guys do it. It's open anyway. I asked 11 questions on it, basically about like the different types of particles, the types of penetration, and about the nuclear stability based on the ratio. What's the desired ratio? 1 to 1.5, so from small to large atoms, right? Okay, so if we get to that, we probably won't. I can guarantee it. Okay, so for the seesaw shape, visualize what it is and tell me with your words, with your location words, where the bonded parts are and where the non-bonded parts are. So 4 ligands and lone pair, but where?
2 going this way and 2 going the other way.
Okay, stand it up straight. Stand up straight in your head and tell me where these are. What's that on top word though? Axial, that's what I want you to tell me.
Oh.
Okay, so there's 2 on the axial plane and then there's 2 on the
equatorial plane.
Less than 120 degrees.
Because
The lone pair pushes.
Alright, you guys are really good at visualizing this, those of you answering. So we've got our axial top and bottom because you got to talk, I mean, if you're going to write out something, you'll be drawing some Lewis structures on the exam. I can guarantee it for the free response. But if you can talk through it too, it makes you sound like you are like Einstein, okay? I need you to say those words again. So you've got your, so here's your central atom, you've got your axial, and then you've got your equatorial. Oops, that one's supposed to go back, but whatever. There that is. And we've got our huge lone pair over here that's taking up a lot of space, repelling the equatorial one, so they have a little less than 120, but still, what's the angle here? 90 here, 90. So this is about 120. Okay, awesome. What's the only difference about T-shaped? Right, so you're not looking at your notes, right? You know this? Yeah, so we got 2 lone pairs, we got 1 atom, or 1 bonded atom, and that's the only difference. For the trigonal pyramidal, what's it look like? Three ligands.
3 ligands. There's 2 on the axial and maybe 1 on the.
This one doesn't really have a great axial equatorial naming system.
It makes like a triangle when you make like a pyramid out of it, and
okay,
then there's lone pairs, I think.
There's
right?
1 pair.
Yeah, there's 1.
There's 1 lone pair. And we draw it like this, right?
Yeah.
So it's got lone pair on top, leg, leg, leg. Trigonal. 3 legs. Okay. So 1 in the plane, 1 coming out of the plane, 1 going back, and then a lone pair up. That's not great. Question?
If there is no lone pair, would it be trigonal?
Yes, because there would be no pushing, which the repelling part's what's causing it to stand up. But if it's not, then it's just going to be flat. So an example of this one. Give me a compound.
BF3.
Okay. BF3 actually could work for this one, but it doesn't have a lone pair. So let's go ammonia here, and then this one.
F4.
Thank you. All right, so I'm going to talk to you about hybridization at the end of class because I want to let you build and really get your nomenclature in honors tomorrow. It gets your bonding together so that you can visualize the molecules, tell me how many ligands, aka bond, and lone pair. But also I want you to start thinking about how many electron domains you have around the central atom period, because when we do hybridization, that's like the key thing on how you hybridize. I'll be drawing a lot of hybridization stuff at the end. That's what that junk is on the board, but we'll get to that. So let's say groups of 2 or 3, take about 30 minutes. As you get stuff bonded and you want to show them to me, I'll come and check it off on one person's paper, and then I'll just sign all your papers to let you know I'm good with all your bonding structures. The one that says inorganic is the best kit to use. That's what you used in honors chem. The other one is a AP level kit. There's like 3 molecules that you can build with it. So it's rather useless unless you only have to build 3, but you guys have to build like 12. So as you go, deconstruct what you need to, but on the central atoms, you need to make sure you have exactly the number of holes you need. If you need 4 ligands and that's it, you need the one with 4 holes. If you need 4 ligands and 2 lone pair, you need the one with 6 holes. So just make sure you're choosing the right one so the shape comes out the way it's supposed to, okay? All right, go at it. Don't mix up the kits, please. So, oh man. Hold on. Get ready for me. Start. Yeah.
Soccer.
Yeah.
Yeah, sport.
Yeah. Okay. I just remembered that. That was funny. I forgot silence out of it. Okay, so if I wanted you to tell me how many bonds are on methane?
4.
4 bonds, right? How do those 4 bonds form? What are the electrons involved? What electrons from carbon?
Oh, the valence.
Valence electrons from carbon. Here's my valence electron configuration orbital diagram for those valence electrons. Yeah.
Yeah.
One in the 1s. I'm sorry. There's actually two. There's actually two here. But what happens is carbon has 2s2 and then 2p2. But when it wants to bond, it's trying to create an equal environment for all bonds. So it promotes an electron to that third orbital in the p subshell. Yeah? Okay, so this is going to allow for 4 bonds. So there's going to be 4 bonds forming. One that's going to share and fill this one, fill this one, fill this one, and fill this one, so that carbon has octet. That's the goal of all atoms, so that they can attain octet via bonding, right? And hydrogen only has one because it's got that 1s1, and so when it shares with with carbon, it fills its one to the duet. Good so far? Okay. So how many electron domains are around this? 4 electron domains. So how many orbitals do I need for these electrons to live in? 4. An orbital holds how many electrons? 2. So each of these bonds are representing an orbital, a filled orbital. So a bond is simply an orbital that's filled. Got me? Okay, so if I need 4 electron domains, aka 4 orbitals, what are the 4 shapes of orbitals? Okay, give me the shape. Sphere, dumbbell, double dumbbell, flower. Okay, the 2 simplest ones are sphere and dumbbell, right? All right, so a sphere looks like this. A dumbbell looks like this. If I wanted to show you how these orbitals form, I would have to show you carbon with an s orbital around it, sphere, right? H with its s orbital around it. That overlap region is where the electrons live. One's coming from carbon, one's coming from hydrogen. Okay? The other ones would be not S, because at this point I've already used up that one S-shaped orbital carbon has, and now it's got 3 P's. So it's got a dumbbell, 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 and then there's 3 hydrogens with circles, right, with spheres. And so it'd be like circle, circle, circle. Okay, that looks awful. It looks horrible. It looks like a 4-year-old did that. Okay. So what's happened is I'm showing you there's an S and S orbital, and then there's a P and S orbital. But in an experiment that they've done, they've shown that every bond in methane are identical. Do I show you identical orbitals over here, or bonds? No, I'm showing you one that's an SS, and then one that's an SP. SE, SP. So what I'm showing you is incorrect. So I can't draw orbitals like this. I have to draw them so it represents each of the bonds of methane being identical. So what I can do is I can blend 2 orbitals. I can blend an S with a P. So a blended S with a P looks like this. I'll draw it over here actually. So you see this little notch back here? That is the small part, which represents kind of the S part. I don't know what that is. Something logged out. Nathan's ortho appointments morning. That's what I put on my calendar. Okay, am I still videoing? Yeah, okay. So back here, when I hybridize, I blend orbitals. So this big, huge red thing right here is a blend between S and P. Do you see how it's a blend between S and P? S by itself is a sphere, P by itself is a dumbbell. If I push them together, it takes on this like half S, half P shape. I just knocked off like half the orbital, the dumbbell. And so that's one. Here's the other one. 2. Here's the other one. 3. Here's the other one. 4. So that's what a blended orbital looks like. Okay? These blended orbitals have names. There are 4 of them. So how many regular orbitals do you think I had to put together to make 4 new orbitals? 4. I took 4 atomic orbitals, 1s and 3 p's, and I mushed them together, blended them together to make 4 hybrid orbitals. Okay, so I took the 4s, 1s, and then 3 p's. I took all 4 of those and I made it a hybrid. So this hybrid is called sp3. Why? It has 1s and 3 p's blended together. So what do you think it would be if I took 3 atomic orbitals to make 3 hybrids? sp2. Because I still have to use an s, because the s is the very first thing you see in the valence shell. You see that s2, that first shell is filled before you can even proceed to the p's. So right now, methane, what I would do is I would say label the hybridization of the carbon in methane. This carbon has 4 electron domains. 4 electron domains require 4 atomic orbitals. 4 atomic orbitals make 4 hybrid orbitals. And then 4 hybrid orbitals correlates to sp3 hybridization. 4 comes up every place here. See how this s has a 1 exponent? 1 plus 3 is 4. That is the trick to the trick. If I wanted you to have 3 electron domains, I need 3 orbitals to fill the places where the electrons are living. Okay? And those 3 will blend together into 3 hybrids. And then that would be called an sp2 hybridization because 1 plus 2 is 3. So it's all based on the fact that you know what the Lewis structure looks like, and then you can say how many electron domains it has. That's how you can tell the hybridization. I have a lot of notes on this too, but yeah, go ahead.
When you were blending, I don't understand the little thing is. Like,
It's a really goofy little ugly knot. It's supposed to represent the part that's representing the S part of it. So instead of having a nice big figure 8, it's got... Oh, I'm sorry. This part over here, I forgot to explain this part. This part over here is representing the fact that hydrogen only has accessible, you know how it's just 1s1? It only has an S shape available to it. So the S orbital from hydrogen overlaps with the sp3 orbital from carbon. So the overlap is where the electrons exist. This little area right here. So I draw hydrogens separately because the only thing I've actually hybridized is the orbitals from carbon because it was s1p3. Okay, so I would call carbon sp3 hybridized. Give me an example of something that would be sp2 hybridized. Something with 3 electron domains. You just built one. I need a structure. Compound.
SP2?
I need sp2, yep. Huh? BF3 is good because it's boron with 3 legs, 3 electron domains. Give me something that's sp2 hybridized. Meaning I only have, sp orbital hybridized, which only has 2 electron domains. I need a compound.
Water.
Carbon dioxide. Water is actually sp3. See how water has a hydrogen, and an electron pair, pair? It's got 4 locations of electrons, so 4 electron domains. 4 electron domains is sp3. Alright, I see some okay faces. Let me go into a little more detail, and then we'll talk about how to do it by ourselves. Alright, so we all know theories are theories. They are here to support things that we've seen in the lab. We've seen experimentally. And so we design theories to fit this until someone disproves the theories that we've had. Well, what's the first theory we learned that tells us the shapes of molecules? The Vesper theory, the valence shell electron pair repulsion theory. It tells us that they push things away and they make these funky shapes like seesaw and T-shape. But that whole Vesper theory does not explain double bonds very well. So we've come to a conclusion that there's other models out there that we need to explore. The first one we're talking about today it's called the valence bond theory. It deals with hybridization. And then the other one we're talking about tomorrow is the molecular orbital theory, which talks about delocalized electrons, which we're going to call pi bonds. So don't write down a whole lot on this one, but this is one we're talking about today, the hybridized theory. And I explained a lot of it, but I want to show you pictures and some more reasoning behind it. So, like I said, the best rule is really helpful in telling us the type or the shape, but it doesn't actually tell us anything about why the bond forms. Why the bond forms is this right here. There's an overlap of two orbitals, each of them carrying one electron each, which makes a shared bond. So what I'm saying here is this is probably the most important thing to write down if you don't have it already. I can't remember what I copied on your papers. So when I draw C bonded to H, what I actually mean, yeah, there's two electrons there, but what I actually mean is carbon has an orbital and hydrogen has an orbital, and this shared space right here in the middle is where the two electrons exist. That's what a bond is in this theory. So in the lab, they've seen that, for methane, that's the prime example here. For methane, each of those four bonds are identical. So not only do we have to think about where they are, whether they look like, what orbitals are overlapping. If they're identical, we have to come to a conclusion of how did they become identical. That's where the hybridization comes in. That's where we blend a shape. We morph the shapes. The S nice sphere shape and the P big double dumbbell shape, we morph them into that little funky orbital like that. That's what the sp3 orbitals look like. Okay, so this is on your sheet, I think, right? Double check for me. Is this on your sheet, your notes sheet? Somebody look for it for me. But this is what I told you earlier. However many atomic orbitals, this should be in the lower right-hand corner. However many atomic orbitals you have, I call them the native atomic orbitals. It's just naturally what each atom carries. That's how many hybrid orbitals you have. So the key to all this information here is that whatever your number of atomic orbitals you have, you're going to make the same number of blended orbitals or hybrid orbitals. And how do you know how many atomic orbitals you need? What I say was the starting point? Right, the number of electron domains. So that's the starting point you should know. And we don't blend these orbitals willy-nilly. We don't hybridize just any old orbital. We have to think about the fact that all bonding is an energy-lowering process, right? Things bond because they want octet and because they want, as a whole, become more stable. So, you remember a little off-ball diagram? It looks like this: 1s, 2s, 2p, 3s. It goes up. That's called off-ball's diagram. We don't blend like 1s and 3s. We blend the stuff that are close in energy, so that's why I was blending like 2s and 2p. Or I could blend 3s and 3p, and so forth. You blend stuff that's really similar, so you don't blend really wacky things. That's why you're usually always going to see s's and p's, and then we'll get to one complicated one that's s, p's, and e's. But we won't draw those because those are ridiculous. We'll draw the easy ones. Okay, so the type of hybrid comes from the different single orbitals that come together. So the sp3 hybrid comes from one s plus another p plus another p plus another p, right? So this one's going to look a little bit more p-like, so it's going to have like a big humongous lobe, whereas maybe something like s and p or sp hybridized only has an s and a p that comes together, so it might be a little bit more like long spherical. Its shape alters a little bit, but we don't change the shapes because it's too hard for me to recognize what the heck you're drawing. Yeah.
If we're talking like when you say sp2 orbital, do you need to put the number of that orbital?
No, it doesn't matter. All I'm talking about is the valence shell, and it's understood because that's the only thing that's involved in bonding. Okay. All right. I'm gonna come right back to this because I have a better picture for you. So this is what I showed you earlier. Carbon's 2s, 2p2. One of them gets promoted to be over here versus over here in the S subshell. So that's what you see here. So what happens is, this is the little off-ball diagram I was trying to show you. This 2s and those 3 2p orbitals hybridize to a happy medium. See how you've got low energy and high energy? They come together at a medium energy. And so they're all identical in terms of their energies and shapes. So you see how we have an S and those 3p orbitals? They come together from those 4 sp3 orbitals. Are we okay so far? It morphed the shapes. That's what's happening here. morphing the shapes. And that's all that up there what that says. Yeah.
If it was, if it had two S's in it, what would the little morph things look like?
It wouldn't have two S's because the S's can hold 2 electrons, and then after that we go straight to P. We don't go S to S to P6. We go S to P6. So that's just not the energy order. Basically, it's all fault diagram. All right, so that's what the morphing means. That's what all this up here says. I'm gonna go back real fast. So I told you about the 4 identical bonds. I'm kind of repeating myself a little bit here, but just want to make sure I cover everything. The other important thing on this slide is that we thought originally it would form, the S-shaped sphere orbitals in the P, but then that's this is actually the fact that occurs. It forms those hybrids that are all each identical, and that this is kind of a theoretical statement, but a molecule is not simply a sum of its parts. Everything has to kind of give and take to attain the lowest amount of energy, this most stable configuration, most stable arrangement of electrons as possible. So that's why we have this hybridization theories, because it explains a little bit more about why some atoms are extremely stable and why others are not, or why some molecules form and why others are not. Like this explains why this does not form, but methane does form, or methane CH5, why that doesn't form. It helps explain a lot of the stability and the possibilities of atoms or molecules. So it's just like you have to think about compromising for the entire molecule, not individual atoms. The theory is a lot of words. The statement of saying what's the hybridization, all you're saying is sp3. That's it. Okay, so I think the answer is easier than the theory. That's why I'm going to show you the answer first. All right, so this is and this is I've shown you the picture here already before, so I'm going to skip over this. What I really want you to see is the effective pair. So you'll hear me say effective pair a lot, not electron domains. Electron domains and effective pair are exactly the same thing. It's just been another word to say exactly the same thing. We like a lot of the same things for some reason in chemistry. So when I say sp3 hybridized, that means there's 4 electron domains. Why is this one sp3 hybridized? Methane? Ammonia?
There's like
No, 4.
4 domains, 3 bonds, right? And 1 lone pair. 4 domains total. Still, you would say nitrogen is sp3 hybridized. Okay, is hydrogen sp3 hybridized? No, it's just still a sphere. It's still one S. It is not hybridized at all. You only hybridize when you're bonding with multiple partners, not just one partner. Why is water sp3 hybridized? 4 domains or 4 effective pair. Even though, yeah, you still say the shape is tetrahedral, trigonal, pyramidal, and bent. Each of these are still carrying 4 domains, so they're each sp3 hybridized. Okie dokie? Yeah.
has 4 electron orbitals, because I would just kind of use the nitrogen because it has 2s2, and if it promoted it, it becomes less stable.
But nitrogen becomes less stable, but the molecule becomes more stable. It's more about the molecule stability and that it's going to be forming and staying and not decaying automatically like nuclear decay, but that as a whole, everything donates to make the whole a more stable thing. Okay. All right, so, and this is what it looks like on the bigger scale, S, P, 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 and then there's the little weird looking orbitals, and then they come together, they look like a sphere, which is why we have to draw atoms as spheres. Yeah.
On the intake exam, what did we say for effective pairs, or what did we say?
Electron domains, either one. Doesn't matter. They know what you mean. All right, let's go to sp2. Yeah, okay. So how would you draw that Lewis structure? Ethylene. Okay. Uh-huh.
Double bond in the middle.
Thank you, a double bond. Great. Okay. How many electron domains on carbon number 1? 3. Areas where electrons exist. That double bond is still right in the middle. There are only 3 areas. Don't get the double bond confused. There's an area here, and an area in the middle. So 3 electron domains yields an sp2 hybridization. You just add up your little exponents and say there's 3 and there's 3. All right, so how does this look? We all know carbon has 4 valence electrons, right? Here's a valence here, here, and here. I told you about the electron promotion already. That's how we went from sp or 2s2 to p2 to what this looks like. How many of these are actually needed for bonding? Not up front. Since we have 3 electron domains, we need 3 orbitals. So we need these 3 orbitals right here. What's left out? One of the p's. And that's okay, I'll tell you why. We need these 3 to form take the 3 atomic orbitals to morph them into their hybrid orbitals, which is why we get 3 of the sp2 hybrids. But then we still have this random high energy 2p orbital that we can work with. We can put electrons there if we need to, and we do need to. We need to put them in here because these are what's formed double and triple bonds. Only unhybridized orbitals are allowed to form double and triple bonds. These are going to form single bond, single bond, and single bond. And then you're going to have this weird orbital that stretches, that's not hybridized, that stretches up and down. Doesn't that look like a p orbital to you? These are dumbbells. This is going to allow for the double bond to form. I'm going to draw you a picture of this better in just a second. So you need to know 3 effective pair sp2 hybridized. And there's 1 unhybridized p orbital that is allowing for multiple bonds. So I'm like highlighting the important parts here for you guys, okay? Yeah. I'm going to show you the other one in just a second. They're identical, so they hybridize identically. All right, so if I were to draw this, and this is the fun part, okay? Here's carbon, and here's carbon, right? Carbon's got 3 sp hybrid orbitals. So I'm going to draw all 3 of them. There's a little ugly knot. There's 1. There's the ugly knot. 2. And here's the ugly knot. 3. So there's 1 pointing that way, and in. Okie dokie. I'm going to do the same thing for this carbon. Here's the overlap for the first one. What exists in that overlap? How many? 2. Okay, there's 2 electrons. Here's another little ugly lobe. Here's the third one. So this carbon here is sp3 hybridized. This carbon here is sp3 hybridized. What's overlapping with it out here? We're drawing ethene, thankfully. Hydrogen, right? So here's hydrogen. Here's hydrogen. Hydrogen doesn't get hybridized. It's just straight up circle, sphere. Okay. Each of these bonds are overlapping 1 time. So how many electrons are in the overlap? 2 here, 2 here, 2 here, 2 here. How many electrons have I drawn so far? 2, 4, 6, 8, 10, right? How many does this one have to offer? 8, right? Or no, hold on. 4. Oh, yeah. 16, thank you. Hold on, 8. 16 electrons. Okay, so 2, 4, 6, 8, 10. Okay. The other ones are going to be in the unhybridized p orbitals. So this is all in the same plane for now. I'm just going to draw it as if it were. There's 1 p orbital going up and down here, and 1 on this one. Because like I said, carbon has an extra p that's not hybridized. So we draw it big and broad, okay? Their shape is not changed. The overlap for this doesn't actually overlap. We have to draw it overlapping. What happens is you just draw like a little archway on the top p and on the bottom p. So each of these p orbitals on the left and the right are going to be sharing 1 set of electrons. So you draw 1 up top and 1 down low. So this is actually a double bond. Why is it a double bond though? Because how many electrons are in the center?
4.
1, 2, 3, 4. A double bond is made of 4 in the middle. That's why it's whatever I said it is. And this is not 16. Is it 16?
Is carbon 6?
4 valences. 4 valences, 8. Well, where's the 12th one? 2, 4, 6, 8, 10. Oh yeah, 12. Okay. I was like, this can't be 16. Carbon has 4 valences, so 4 times 2 is 8, plus 4 is, I don't know either. I was agreeing with you. All right, so we got 2, 4, 6, 8, 10, 12. All right, so what you need to know is when I say single bond, this is the way you identify it. It's like a little baby. You know, you draw like a little baby like that? Go ahead with the squiggly line. All right, you just learned how to draw a baby. Okay, so this is called sigma. Sigma is what you call a single bond. So all this blue here in the middle are single bonds. The p orbitals, p makes a pi bond. So this has 1 pi bond. It's actually the letter pi. So p orbitals make pi bonds. The pi name is supposed to represent p orbital shapes. And the sigma name comes from the S, the S morphed shape. So this double bond is made up of 1 sigma plus 1 pi, plus 1 pi. So a triple bond would be made up of what? Sigma plus 2 pi. To make 3 bonds in the middle. This has 2 bonds in the middle. One more? Fun stuff? Okay. And this is what I just showed you. I'm going to skip this for now. All right, so if I have 2 effective pair, example carbon dioxide, C double bonded O, double bonded O. All right, so 2 effective pair, 2 electron domains, sp hybridized. What's actually doing the hybridization here? Huh? What from carbon?
Oh, the 2s and then 2.
Just one of the p, right? So just these 2, leaving us with 2 empty p orbitals, which are going to allow for us to double bond, right? Why do I need 2 of these guys to double bond? Because there's 2 double bonds. So I need to overlap on this side and overlap on this side to form both double bonds. Okay, so carbon dioxide, we've seen before. What do you think these little lines on top and bottom actually represent? The pi overlap. So there's 1 overlap on top and 1 on bottom. But you see how this one goes out at you and back at me? These pi bonds cannot be in the same axis because there's 3 axes of where the p orbitals can go. They can go up and down, they can go out, and they go side and side. So when I draw this, you're going to have to work with me on the 3D shape. So I've got 2 sp and I've got 2 empty p's. All right, so let's draw carbon dioxide. I just need some space for this, so I'm going to go all the way down. And these pictures I thought would be helpful, but we're essentially drawing them too. So here we go. Carbon in the middle, oxygen, oxygen. Carbon's got how many hybridized orbitals? 2 hybridized orbitals. Carbon's sp. Here's one of them, and here's the other one. All right, so those are my sp hybridized carbon orbitals. Carbon also has what left over that didn't get hybridized? 2 p orbitals, which will form 2 pi bonds, but 2 p orbitals. I'm going to draw one in the up and down axis, and I have to draw the other one in a different axis. I'm going to draw it coming out of the board. You just kind of bolden it so it's coming out of the board, and then dot it to show that's going behind the board. We're going to use those p orbitals in just a second, but I'm not there yet. Oxygen is what hybridization? Look at oxygen. How many electron domains around it? 3, 2, 1, 2, 3. So what's its hybridization? sp2. So it's got 3 domains, right? So I need 3 sp2 orbitals around each of these oxygens, yeah? Okay, so here's the first one, overlap. The second one is going to be existing as a lone pair. That's just the third one. Huh? Huh?
I thought they were sp.
Yeah, I get lazy now. Like, they're not. Thanks, Lexi. I don't like to. It's just tedious, and you can write it, but they don't. I mean, they don't actually look for it as often. They just look for the overlap and the fact that you have the correct hybridization. There you go. So two lone pairs, overlap, overlap. Because these so far are representing a sigma or a single bond and a sigma, aka sigma bond. Yeah. All right. So then I'm gonna put my electrons in here. This is like so fun for me. I don't know if you guys realize this. It's my favorite part. Okay. So now all I have to do is finish it off by putting double bonds, which are overlaps of p orbitals. Yeah. So let's still not draw on each of these oxygens. A p orbital, because anytime you have sp2, you still have one unhybridized p orbital, right? One of them has to overlap with this one. So I'm going to draw in red because they have to be in the same plane to overlap. So here's the first one, overlapping. There's one electron up here and there's one down here. This oxygen's p orbital has to be oriented in on the other axis so that it can effectively overlap with that one. I'm going on top of that lone pair, but it's okay. Looks kind of 3D, right?
That was really 3D.
I'm trying. But the goal here is that pi bonds cannot form unless p orbitals are parallel. Sounds like I don't know, p or whatever you call it with all the p's. Pi bonds cannot form unless the p orbitals are parallel to one another. So they have to be in the correct axes. And guess what? Carbon dioxide has no rotational ability on this axis. See this pi bond here? Locking it in place. It cannot turn. Whereas water, turn, it rotates the whole time on its little bond. This is stuck. So why do you think cis and trans exist? Can it move them? Yes, those are called structural isomers because the pi bond here keeps this cis like this. It can't rotate because the pi bond that's holding it together is forcing it to stay as cis. And the trans one is keeping it as trans. There's no rotational axis here because this pi bond has this little funky p orbital overlap that won't allow for rotation, just free rotation. So that's why we have isomers that are structurally different because of their locations. Got one more or two more for you. I'm not going to draw these. If you have 5 electron domains, you can't go past P3, so you have to go into the D's now. Okay, because each of these little exponents are representing number of orbitals in this case. So we have sp3d. Add up those exponents, what do you get? 5. So sp3d, 5 electron domains equals sp3d hybridization, which is usually trigonal bipyramidal. So give me an example of that one. Thank you. sp3d2, 6 electron domains. Give me an example. SF6, yeah. So you've done all this before. Now all you're doing is telling me what the hybridization is for the central atom based on the number of electron domains it contains. Don't ask me. I have no idea. Oh, I can generally how this one's drawn is just like normal. Cl, 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 but Cl has its own little hybridizations. They're not circles, they're sp3 hybridized. So like, it's PCl like that, right? Up at 5 times. So P is sp3d hybridized, and Cl is, how many electron domains are on Cl? 4, so it's sp3 hybridized. You can recognize the hybridization on every single atom, except for hydrogen because it just is us. No, you won't have, and it doesn't even look like that. I won't ask you to draw those. If anything, I'll ask you to draw the easy 3 that we did. Not easy, but the ones that we did that are easier than those. And so that gives off the hedral arrangement. This is kind of how they just show you how the shape works out. And occasionally you'll see the D before. It's like or it's DSP3 or D2SP3. It's just another way of writing that hybridization one. I have one more slide for you and that's it, okay? Just on bonding, because I already talked about sigma and pi, but I just want to let you see some more details. This I was going to have you add to your notes, but do you think you can do this if it's linear, two effective domains, so it's SP? If it's trigonal, SP2, it's tetra, SP3, if it's orbital, it's got the D's. No, I'll go back to this for you. I went through all that for you. I'm not going to go through that again. I have a lot of summary slides. This is the only other thing this is on your notes. I've not actually shown you this. I didn't say the word internuclear axis I meant to earlier. The sigma bond exists directly between two atoms, so it's called internuclear because it's between the nuclei, right? So that word internuclear refers to vast overlap. Like this carbon is really overlapping with this carbon. So this high amount of overlap allows for a strong sigma bond. So do pi's overlap very much? No, it's like, here, I'll start checking it. It's like, that's it. They barely overlap. But sigma's like, overlap, okay? This one's really strong. This one's very weak. So you can break a pi bond, that overlap that's on top and bottom, relatively easily. So that's why I have sigma bonds are stronger than pi bonds, because of the overlap. And these are formed by sideways overlap of orbitals. So the electron densities are on top and on bottom, not between the two atoms. Prevents rotation, I talked about that. Yeah. I think I said this stuff, but you've got it written down so that you can highlight and do what you gotta do with it. Hybridization not horrible. Good question.
Atrocious.
The answer is not atrocious, but I actually didn't fully understand this until I started teaching it. I knew how to hybridize something. I was like, oh yeah, it's got 4 electron domains, SP3. I acted like I knew what I was talking about, but I didn't know that until I started teaching it. So it takes a lot to fully understand some of the theories and stuff, but I just wanted to let you know this is on your paper, and I told you that double bonds have one sigma and 1 pi, and then triple bonds contain 1 sigma and 2 pi. Those will be easy multiple choice questions that you should be able to answer very quickly. All right, so what if I wanted you to tell me the hybridization of each of these? I'm drawing acetic acid, by the way. Here's acetic acid. What's the hybridization here?
SP3.
SP3. Here.
SP2.
SP2, because there's only 3 domains. Here. SP2. Thank you. Here.
SP3.
SP3. There's no words. SP3. That's what you have to do. You can do that. After you draw the structures, I believe in you. Okay, I suggest you study for the quiz that you're going to have on nuclear. If you haven't gotten your stuff, there's a couple packs of papers over there. The nuclear quiz will be maybe tomorrow, maybe I'm going to try to do it tomorrow, because we have a Lewis structure, geometry, and hybrid quiz on Wednesday. These molecular problem sets, 7, 8, 9, 10, 13, and 14 are the more complicated ones. I suggest you do that. Ask me questions if you need to. I'm not taking this up. That does not mean not do it, because I don't want you to fail your quiz and then eventually not do hot on your test. So I'm giving you some optional homework so that you guys can sleep, because your homework for this week is to log your sleep hours.
Are you serious?
What?
Oh,
On Friday, I want to know every day, Monday through Thursday, your sleep hours.
I got
Do not lie to me.
So,
Do not lie to me. I need the truth and only the truth, so help me God.
Do you want to
Okay.
know when they go to bed?
Yeah, like 8 to...
8.
8 Right. So that's what I need from you. But tomorrow, the hybrid. Once you get the hybrids and once you get Lewis structures, I'm just like wasting your time making you draw more. Yeah. Because once you get Lewis structures, you can draw any Lewis structure I give you. So I want you to practice the rest of the ones on the reading guide too, where I said fill out the hybridization, because you've already listed all the electron domains on those, yeah? So just go and fill the hybridizations in, and then if you would like to attempt more on that village problem set, that's study evidence for you. By all means, do it. But ask me questions on those. Those are the hardest ones. So I'm not taking that up tomorrow. I'm only taking up the reading guide part 2, and actually part 1 and part 2 tomorrow. Okay?
What's the last
Lab not, but no, it's not due until after our tie-dye lab. Yeah, it's little bitty one. 18 problems.
Do you want to take something?
I'll look. Hold on. Oh, we still have 4 minutes left. All right.